Good morning. So we are in the third module about shear force and bending moment, and we have seen some problems related to simply supported beam and cantilever beam, one cantilever beam. Okay. Now, before proceeding with further problems, we'll go through the relationship here. Okay. This is a relationship between the load intensity, shear force, and the bending moment. Okay. For that purpose, this is a beam what I have taken here. Okay. So right. So this is what the beam is, and this is of span L. Okay. So what we are actually finding out is what is the relationship between the load intensity W, shear force, and bending moment. Okay. Right. We'll look into this relation here. Okay. For that, this is a beam, and the span of this beam is L. Okay. From one support to another support, the distance is L. Okay. And what we have is on this beam there is some general loading which is applied. Okay, you can see the variation. We don't know how actually is the variation of this load, so we call it as a general loading. It may be UDL, it may be uniformly varying load. Okay, or it may be this one other type of varying loads. Okay, so but what is there is this load intensity is a function of x. Okay, meaning with increase in the distance, there will be increase in the resultant load. Like our UDL. UDL is a function of x, 10 kilonewton per meter. That is function of x. So with distance, the load, total load will be changing over there. Okay. So like that, this is a function of x over here. W of x. That is the load intensity. So this is the beam, and this distance AB is L meters. Not just meters, it is just L. Okay, it may be any unit. So here, what is done is, I'll go for choosing a section somewhere within the span over here. Okay. So how do I choose this section is, I'll consider some small section over here. Okay. So these are the two sections what I have taken. Let us say this is dx. Okay. So I'm going to take out this portion of the beam. Okay. So between 1, I'll call this as section 1 1. Sorry, this is 1, and this is my section 2 2. Okay, so this distance between section 1 1 and 2 2 is dx over here. okay, a small distance x on the span of the beam. So when I do that, when I take out this section, how the forces are acting on this section are shown over here. Okay, so on the left side of this section, this is my section dx, which I have taken out from that beam. Okay, this is a small element over here in the beam which I am considering. So these are the forces which are acting on this section over here. On the left side, you have a shear force F. Okay, on calculating, we'll get to know what is the shear force F. Okay, so and in addition, there is a bending moment M applied on the left side of my section. Okay, on the right side, what we have is shear force will increase by F plus dF. Okay, there will be a small increment in the shear force. Let us say it is F plus dF over here. And in the same way, there is a small increment in the bending moment. Okay, we'll take it as M plus dm. Okay, dm and df, these are the small increments in the shear force and moments. Okay, and if you look at the loading which is coming on this portion dx, so for this small portion you can take this load to be uniform. Okay, since this distance dx, what we have considered, is very small, so its variation, the variation in the load, okay, whatever is there, it may be linear in case of UL, constant in case of UDL. Okay, so that can be taken to be same from one end to another, and I'll assume that to be constant. Okay, I'll assume it to be uniformly distributed load like this. Okay, so its intensity will be W. Now, if I want to know what is the total load over here, I'll have to multiply W by this length dx. Load intensity W by the length dx over here. Okay, so to get the total resultant load, W into dx. Okay, so this is the load what is applied on this section, right? Now we'll take up the equilibrium of this section. I'll go for considering the equilibrium of this particular section. So for equilibrium of the section, I can call it element. Okay, so what it has to satisfy is, it has to satisfy summation fy should come out to 0. Okay, summation fx is not considered because there is no horizontal load over here. Okay, so I will not go with summation fx. It is automatically satisfied due to absence of the horizontal loading on the beam. Okay, so first condition of equilibrium what we'll take is summation fy equal to 0. So what are the forces in y direction, in vertical direction over here? So in this vertical direction, what forces are acting? This is our coordinate x and y. So in the y direction, we have F, okay, which is acting upwards. So F, we have this load which is applied on that element. So total load, resultant load will be W into dx, and it is acting in downward direction. So minus W load intensity into dx. Okay, and on the right side, what we have is in the vertical direction, in y direction, this is the force F plus df, and it is also acting in downward direction. So F minus F minus df. Okay, so this is what I have. So this should come out to 0. Okay, you can put it in one bracket also if you want. The entire load on the right side. This is from the entire load which is there on the right side over here. This will be F plus df minus F plus df. Okay, or what it tells me. So this gives, on rearranging, if I rearrange the terms, okay, so what I have is df upon dx will be equal to minus w. Okay, f and f gets cancelled out, and if I take this df on one side and again dx on the other side, this is what the relation I'll get. Okay, so this is one of the first relationship for here between shear force and the load intensity. Okay, so what it tells, So it says that slope of the shear force diagram is equal to the intensity of the load. Okay, so this is df by dx is nothing but slope of your shear force diagram. We used to draw the shear force diagram. If you find the slope of that diagram, so it will be giving you the intensity of the load at that point. Okay, load intensity. Okay, this negative sign will be indicating that the shear force is decreasing with the increase in the x. With increasing x value, your shear force will be decreasing. That is what this negative sign indicates. So what we did for that is we wanted to establish the relationship between load intensity and shear force. Okay, so we have taken a beam, okay, of span L meters, anything L, and this beam is subjected to a uniform this general loading. Okay, general loading means the load intensity is a function of x. Okay, we may have UDL present on it or UL present on that. Okay, so this is a function of x. That is the important thing. The load intensity is a function of x. So with that, I went for considering two sections within the span of the beam, section 1 and section 2, at a distance dx apart. The distance between these two sections is dx. Okay, so I have taken out this element dx outside of this beam. Okay, and I'm showing the free body diagram of that element. Means I'm showing all the forces which are acting on this element dx. Okay, now on left side, what we assumed were moment, what is acting is m. The shear force is f. Okay, and on the right side, the moment is m plus dm. It is increasing by an amount dm. Okay, and the shear force is f plus df. Okay, so this is the shear force on the right side. With the increasing x, these will values will change. Okay, we have seen this in our examples also. Okay, and what is the applied load on this element? It is load intensity multiplied by length of this element, w into dx. Okay, for a small length, this load intensity, okay, can be considered to be constant. So that intensity multiplied by dx. For this, we consider the equilibrium condition. The first equilibrium condition is summation Fi equal to 0. Okay, so when I add up all the forces in y direction, in vertical direction, with their sign, appropriate sign, that should come out to 0. Okay, so from this equation, what we got to know is the slope of the shear force diagram is equal to intensity of the load at that point. Okay, this is what it says, first relation. Minus sign indicates whenever there is an increase in x, increase in the distance, the load intensity is reducing. Okay, that is what this relationship says. Okay, further what I can do is, now let us consider this equation 1 only. Okay, on integrating this, I'll go for rearranging this equation 1 and integrating it, okay, between these two sections. Okay, so what I have, so integration df is equal to integration minus this w into dx. Okay, so what this gives me, this is between f1 and f2, between two sections. Okay, f1 and f2 are the shear force at section 1 and 2, and let us say distances are x1 and x2. These are our limits. Okay, so f2 minus f1, okay, this will be equal to integration x1 to x2 w into dx here. Okay, so difference in the shear force between the two sections, difference in the shear force f2 minus f1 is nothing but the difference in the shear force between two sections 1 and 2. So that will be equal to area under the load diagram. Okay, so this integration w into dx is nothing but area under this loading. Okay, so it will be the area under this portion. So the difference in the shear force, okay, or the change in the shear force between any two sections is equal to the area under the load diagram. Okay, So that is what this relation tells us. Okay, let me call this as A, right? So this is what we got over here. From equilibrium condition, we established a relationship between load intensity and shear force. Okay, further, we also got to know that the difference in the shear force between any two sections will be equal to area under the loading diagram. Okay, this is our load. Okay, so whatever the area is there under this load diagram, that will be nothing but the difference in the shear force between these two sections, 1 and 2, or any two sections. Okay, so this is the first one what we have. Now second is, what I go do is I'll go for one more condition of equilibrium. The second condition of equilibrium will be summation of moments should come out to 0. Summation m should result in 0. So what are the moments acting on this section? Here in this direction, what I have chosen is as per positive sign convention direction on this section. Okay, whatever the loading direction we have chosen. So here on the left side, what is the moment? So it is m. Okay, and plus, and on the right side, the moment is anti-clockwise minus m plus dm because it is anti-clockwise. Okay, so what is the moment due to this load? So what I have is I'll take the, let us say, I'll consider moment about this particular point on the left side. So moment due to this UDL which is present on the element. For that, what we get is, so this is the resultant multiplied by dx by 2, and it will have a clockwise moment. Okay, so plus w into dx into dx by 2. This is the moment due to this applied load which is present on the element. Okay, so this w into dx was the resultant, and where it acts at the center of this element. Okay, this is dx by 2 over here. Okay, I've taken moment about this point over here on the left side of the element. So this should be equal to 0. Okay, now in this what we'll do is this higher order term which is of the power 2, dx to the power 2, will be negligibly small. Okay, so I'll just ignore this. So in this, that is dx to the power 2, that will be ignored, or this entire term will be ignored. That is dw into dx into dx by 2. So we'll neglect this. So on doing that, what we are going to get here is okay, in this I missed out the moment due to the shear force here. So one more term I should consider. What is that? So about this point, this force, okay, this shear force, what is there on the right side of the section will have a moment, and it is having a clockwise moment. So what will be that moment? Plus f plus df into dx. Okay, so this should come out to 0 actually. So what are the moments? One is this moment, clockwise moment on the left side of the section m. Okay, and another moment is m plus dm, which is in anti-clockwise direction, minus m plus dm. Due to the UDL, or this load which is applied on the element, the moment will be w into dx into dx by 2. Okay, so this will be having a clockwise moment about this point. Okay, let us call this point as O. So about this O, the moment due to this load which is present on the element will be clockwise. Okay, so plus w into dx by 2, right? And because of the shear force which is there on the right side of the section, that is this f plus df, because of this force, what is the moment about point O? First is it will have a clockwise moment about point O. The magnitude of that moment will be f plus df into the distance dx. Okay, it is acting on the right side of the section, so into dx. So f plus df into dx here. Okay, so I have neglected the higher order terms over here. Even this df into dx will also come in that higher order term. So when I neglect these terms, what I'm left with, so I'll have m over here minus m minus dm. Okay, so this term is gone, we have neglected, plus f into dx. This is what we are left with, should be equal to 0. Or on cancelling, what I have in this case, dm by dx, okay, is equal to f. Okay, so this is another relation, that is our second relationship we have. So here what we can see is shear force between any two sections is equal to the slope of the bending moment diagram. Okay, or rate of change of bending moment is equal to shear force. This dm upon dx is nothing but rate of change of bending moment. Okay, so that is equal to df. If I have an equation for bending moment, okay, m, we can write an equation for m in terms of x. So if you obtain the first derivative of that equation, then that will be representing the shear force, okay, between the 2 points what you consider. Okay, this is one more relation. Is that clear? From the second condition of equilibrium, this is what we get. Taking moment about this point O on the left side of this section, or because of all the forces, what I have, summation of moments about point O should come out to 0. So one moment is this m in clockwise direction. So m, okay, and this moment, what is there on the right side of the section, is in anti-clockwise direction. So minus m plus dm, that is taken here. And due to the load which is there on the element, okay, so what is the moment? The resultant load is w into dx, and it will exactly act at the center of this UDL which is present over here. Okay, so w into dx into dx by 2, middle of the UDL. Okay, so moment will be this load, total load multiplied by the distance. What is the direction? About point O, the direction of this movement will be clockwise. It will have a clockwise movement about point O. So plus w into dx into dx by 2. Okay, and one more force is this shear force, which is there on the right side of the section, on this face of the section, right side face of the section. So it is f plus df. What is the moment of this force about point O? F plus df into dx, and direction is clockwise. It will try to rotate this element in clockwise direction. So f plus df into dx. Okay, so in this equation we have totally neglected the higher order terms, okay, which are very very small, negligible. So higher order terms are these, this one and this df into dx, that will be the higher order term. Okay, so those terms have been neglected over here. Okay, so after doing that, if I consider the equation, so it will be like this, what I have shown here at this here. And in this, if you cancel out the terms and rearrange them, what you will get is dm by dx is equal to f. Okay, what that tells me is the rate of change of bending moment is equal to shear force. Okay, rate of change of bending moment is nothing but it will be equal to the shear force at any section. Okay, or the slope of the bending moment diagram will be giving me the shear force, okay, between the 2 points. That is what this relation says. Okay, further, what I have now, we came to this equation dm by dx is equal to f here. Okay, now if I go for integrating this, let me rearrange this. Okay, so and so what I have is dm is equal to f into dx here. I can write it in this way. And on integrating between section 1 and 2. Okay, so what I have, integration m1, it is the moment at section 1, and at section 2, let us say the moment is m2, dm, okay, is equal to integration f into dx. And this variable is x, so x1 to x2 distance. Okay, so what this gives me, m1, or sorry, m2 minus m1 shall be equal to integration between x1 to x2 F into dx. Okay, I'll call this as B. So from this equation, what you have is change in bending moment at any two section will be equal to area under the shear force diagram between the two sections. Okay, so change in bending moment between any two sections is nothing but the area under the shear force diagram. It will be equal to the area under the shear force diagram. Okay, so like we had the shear force diagram, you can see something like this for a beam. So if you consider 2 points on this beam, so the area under the shear force diagram, it will be nothing but the difference in the bending moment between these 2 points. Okay, we'll see that when we take up the examples, these relationship will be useful to us over there. Okay, one more point what you can note here, right? So when the bending moment will be maximum, if I ask you, so you can say if the bending moment is a function of x, say if we have a equation for bending moment, okay, bending moment in the form of equation, m is a function of x. Okay, let us assume that it is a function of x. We'll come across such equations. So when this bending moment will be maximum, so for maximum bending moment, dm by dx first derivative has to be 0 over here. Okay, so if I differentiate this equation of bending moment with respect to x, and if the first derivative is 0, then we can say the bending moment is maximum. Okay, bending moment is maximum, or it also indicates that at that point shear force is 0 from this equation. Okay, from the equation number 2 what we wrote, this also indicates that where bending moment is like maximum, at that point shear force will be 0 over there. Okay, note this one, this is a very important relation what we have. Okay, for maximum bending moment you should have 0 shear force at that point. Okay, this is when you have load intensity as a function of x over there. So these are some important relationship what we have. Okay, with the load intensity, shear force, and the bending moment. Okay, is that clear? The relationships, two main relationships. What is there is first equation and the second equation. These are the two things to be noted here. Okay. In addition, what you have the condition for maximum bending moment. For maximum bending moment, dm by dx or the shear force EF should come out to 0. Okay. So on this basis, we can find out the section where bending moment is maximum and also what is the bending moment, maximum bending moment. Okay, that can be obtained over there. Okay, so that is what one of the relationship is. And also we came to know that what the difference in the shear force between any 2 points. Here 1 and 2. Say if this is x1 distance, okay, so and this is x2. Okay, so the change in the shear force between the two sections 1 and 2 is nothing but area under the load diagram. Okay, area under the load diagram. Similarly, what we have, the difference in the bending moment between any two sections is nothing but the area under the shear force diagram. Okay, these can be obtained from the 1 and 2 relationships 1 and 2, but most important thing is the first relation what we have here, this one. Okay, and the second relationship, what, this equation number 2. These are very much helpful to us in dealing with problems. Okay, fine. So that is the relation. Please try obtaining or deriving that relation. I'll share this video and this PPT. Try to derive it on your own also. Okay, it may be asked for you in some cases to directly establish the relationship between the load intensity, shear force, and bending moment. Or in sometimes what may happen is you may be uh, using that in our problems. Okay, so we'll take up another problem here. Okay, so let me continue with the cantilever beam. Okay, I've taken a problem on cantilever beam with concentrated loads. Further, let us take a problem with a different loading over there. Let's say this is our beam we have. Okay, I'm facing some problem when I exit that slideshow mode. Okay, so this is what I have, and in this case, we'll have a mixed type of loading here. So what we have is, let us say, there is a UDL. Okay, and at this end, we got a couple, clockwise couple. The magnitude 40 kilonewton meter. Okay, and along with this, there is a concentrated forces which are present on this beam. Okay, so this is one, and one more at this point. Okay, so this is 30 kilonewton, and this is 10 kilonewton. The distance here is 2 meters. This is 1 meter, and this is again 2 meters. Okay, and this load intensity, it is 20 kilonewton per meter with this UDL. Okay, so it is of 20 kilonewton per meter. Now let us mark some points on this one for that, so we can conveniently go for a calculation. So let us say this is A support point, and I'll call this as point P, the first concentrated load where it is applied. Point C, 10 kilometer load where this is applied, and this is free end. It will be point D. Okay, so this is what we have. Now, first thing what we need to obtain is we want to know what are the reactions before we go ahead with the calculation of shear force and bending moment. First is we need to go for calculating the reactions in the beam. So determine or yeah, determine shear force and bending moment at every 1 meter interval. Okay, or let us say we'll just go for finding it. The In this case, let me not take the interval given here. Bending moments in the beam shown. Okay, and also plot SFP and BMD. Okay, so that is a problem. So for solution, okay, what we require is the reactions. So calculate the reactions at the support A, at the fixed support. So in this case, what we have is the supports would be having, it can offer 3 reactions. Okay, so this is one vertical reaction, and along with this, what we come across is the reaction in the form of a movement, and I'll assume that that will be in anti-clockwise direction, and also you have a reaction in the form of horizontal reaction. Okay, so can you find those reaction and tell me what are the reactions over here? Quickly go for calculating these reactions. That is VA, vertical reaction at A, HA, horizontal reaction at A, and MA, movement at A. So what are the reactions? For the reactions, we have support at A. So first is summation Fx is equal to 0, which gives me HA as 0. Okay. Next is summation Fy. Okay. So summation Fy is equal to 0. If I take that, what I have is VA, vertically upward force, minus this 20 into distance is 2 plus 1 3 plus 2 5 meters, 20 into 5, and these two loads 30 and 10 kilonewton, minus 30 minus 10, which are acting in downward direction. So this should come out to 0 here, or VA will be equal to, this is how much, 20 100 130 and 140. So VA will come out to be 140 kilonewtons. Okay, 40 kilonewton. Okay, and the next condition of equilibrium, summation of moments equal to 0. I'll take moment about support A. So summation
Sir,
of,
it is minus 140 now.
no,
So minus 20 into 5. So minus
take it on
140.
right side. Take it on right side.
Okay. Okay, sir.
So here summation of moments about A. Okay, if I take that, I'll move from this end D. Okay, so here what I have is there is a couple which is applied, which is in clockwise direction. So that 40 kilonewton couple, 40 kilonewton meter couple. Okay, so this is a couple 40 kilonewton meter, and my plus due to this 10 kilonewton load, what is the moment about it? This load 10 multiplied by distance. What is the distance? 1 plus 2, 3 meters. Okay, so into 3 meter, and due to this concentrated load of 30 kilonewton plus 30 into 2 meters. Okay, both of them are having clockwise moment about A. Okay, movement is clockwise about point A. Okay, so that's why I have taken positive here. Now finally there is a UDL also here on this beam. So due to that UDL, what is the moment? So that will also turn out to be in clockwise direction. Intensity of UDL is 20. What is the total load due to that? It is spread on a length of 2 plus 1 plus 2, 5 meter. So total load will be 20 into the length of UDL, 5 meter. And if I want to know what is the moment due to this UDL, so this resultant 20 into 5 will be acting at the middle of this UDL length, exactly at the middle. Okay, so it will be at a distance of 2.5 meter from both the ends of this UDL. So I'm calculating moment about point A. So it will be into 5 meters by 2. Okay, so this will give me the moment about point A. So one more is the reaction what I shown here, that should be added to this. Okay, so the reaction in the form of movement MA, which is directly at A, and I assume that to be in anti-clockwise direction. So what this gives me is minus MA, okay, is equal to 0. I've taken the algebraic sum. I added all the moments about point A. Okay, all the moments about point A due to these loads, direct couple, it will come as it is magnitude. It is clockwise 40 kilonewton meter. So 40 kilonewton meter plus 10 into 3 meters. Okay, because this is clockwise, and due to this 30 kilonewton load, the moment will be clockwise about point A. So plus 30 into this distance 2 meter. Okay, and this is due to the UDL. What is the total load due to UDL? So this UDL, it is spread over a certain length of 5 meters. So 20 kilonewton per meter into 5 meter. 20 kilonewton per meter into 5 meter. Okay, where it will act? It will be acting exactly at the middle of this UDL length. Okay, if the length of the UDL is 5 meters, the resultant, this 100 kilonewton, will be exactly at the distance of 5 by 2. Okay, exactly at the center. So its moment about point A will be this 20 into 5 into 5 by 2. Okay, and one more moment what is there is the reaction what we have assumed here at support A, MA, which is in anti-clockwise direction. So that has been added, minus MA. So this tells us what is this MA is equal to. So how much this MA comes out to be? Calculate that. Give me the value of MA.
380, sir.
Okay, so MA is 380 kilonewton meter. Okay, now we'll go for calculating the shear force values. Okay, right? So now I'll do directly the calculations at D. Okay, what is the shear force at D? At this point, shear force is 0. Okay, so shear force at D, it is equal to 0. Okay, come to point C. Okay, I'm taking shear force at C. At C. Okay, so what is the shear force? This 20 kilonewton per meter into 2 meter. Okay, to the right side of this 10 kilonewton load, it is 20 into 2, which is equal to 40 kilonewtons. Okay, and when I move to the left, Okay, I'll take one more section to the left of this point. So there what will happen, the shear force will be 20 into 2 meters, okay, and plus this 10 kilonewtons, okay, which will be 40 plus 10, that is 50 kilonewton. Okay, this is the value of shear force at C when I cross this 10 kilonewton load. Okay, the sign will be positive. Sign as per our sign convention, right side downward force will be positive. Okay, now come to this point B. Okay, at point B, point B. Okay, so to the left of, sorry, first I will be, I'm moving from point D. I've taken point D as my starting point. Okay. In cantilever beams, it is convenient if you take the free end as your starting point. Okay. To the right of this 20 kilonewton force. Okay. So it will be in this UDL. Due to the UDL, it is 20 into 2 plus 3. 2 plus 1, 3 meter. So 20 into 3 meters. 2 meter plus 1 meter. This is the portion of the load which is there on the right side of the section. My section will be somewhere here. Okay, I'm taking algebraic sum of all the forces to the right of the section. So what you have is UDL is present over here for a length of 3 meter. So 20 into 3 plus what, 10 kilonewtons. Okay, this is the only load what I have crossed. So this will be 60 plus 10, 70 kilonewtons. Okay, and when I move to the left side of this concentrated load, okay, to the left of this, sorry, this is 30 kilonewton, not 20. This is 30 kilonewton. So this will be 30. This is 30. What will be the value here? If you have calculated to the left of 30 kilonewton load, it will be equal to the due to UDL 20 into 3 meters plus the concentrated load of 10 kilonewton plus what,
Plus 30 kilonewton.
plus 30. So this will be 60, 70, 30, 100 kilonewtons over here. Okay. Then come to point A directly. What is the shear force here? At point A, before I cross that reaction, shear force is how much? It will be 20 into 5 plus 10 plus 30. Okay, so it will be 100 plus 10, 110 plus 30, 140. Okay, that should be equal to the reaction at that point. Okay, this is what we can conclude. Okay, 40. Once I cross that point, it will reduce to 0 immediately. So this couple will not come in picture when you are calculating the shear force value. This will not do anything to your shear force. Okay, so that will be unaffected shear force values, right? So these are our shear force values. Now, what about the bending moment values? So start calculating the bending moment from point D itself. At point D, it will be how much? Movement at point D. Is there any movement at point D? Any answer for that? So bending moment values. So at point D, Okay, since there is a couple which is directly applied at this point D, so what is my bending moment value? So it is equal to that couple. So it is in clockwise direction, but to the right side of the section. Okay, to the right side of the section. So compare your sign conventions. This is our positive sign convention for bending moment, whereas this is our negative sign convention for bending moment. So we are working on the right side of the section. Okay, so right side, if the moment is in clockwise direction, it is negative. It will be carrying negative sign. So minus 40 kilonewton meter. And at point, what is the point I have? Next is C. So at point C, it will be this couple will come here minus 40, taking sum of all the moments to the right of the section minus 40. And due to UDL, UDL will have a clockwise moment about point C. So right side clockwise movement will be having negative sign. So minus 20 is the intensity of UDL. Its length is 2 meters and it will be acting at the distance of 2 by 2. I'm at point C. So exactly at the center of this portion of UDL, it will be acting 20 into 2 into 2 by 2. Okay. So this will be the bending moment at point C. So what is this? 2 gone. 40 40 minus 80 kilonewton meter. Okay. Then I'll directly move to point B now. At point B, the value of bending moment. So what I have couple it is 40. It will be constant. Okay, throughout the length. So minus 40 right side clockwise movement minus, and due to UDL, so UDL is having a clockwise movement. What is the length of UDL now? It is over a just length of 3 meters, 20 kilonewton intensity, and it is producing a clockwise movement about point B. Right side clockwise movement negative. So 20 into 3 meters is the total load due to the UDL present over there, into what it will act at a distance of 3 by 2 meters. Okay, exactly at the center of this length. So this will come out to be now 40, and this will be how much? 60, sorry, 339, 90, 40 and 90 minus 130. Okay, one more is, now I have this 10 kilometer load minus 10 into what distance? 1 meter distance. So this will be total load moment about point B. How much it will be? Minus 40, and this is 2 and this is 10. Okay, 9 into 10 minus 90, minus 40 minus 90 minus 130, and this 10 minus 140 kilonewton meter. This is the bending moment at point B. So when I come to point A, at point A, what we have? So the bending moment will be, these are all bending moments at these points. So minus 40 is there, couple, minus 20 due to UDL, now it will be 20 into 5 into 5 by 2. Okay, minus 10 into what distance? It is 3 meters. 3 meter, and minus 20, 30 kilonewton. Okay, minus 30. Okay, this is minus 30 into 2 meters. Okay, what this comes out to be? This will be equal to 100. This is how much? Into 2.5, 250, and this is 40, 290, and 320 and 60, 380. So this should be equal to the value of MA over there, kilonewton meter. Okay, or at point A, you can directly say the moment bending moment value will be MA. So all values are negative, indicating that the beam is in hogging. Entire beam is hogging. Okay, so that is what the calculation is. You can please exit by giving your attendance. I have one more class. So if you have doubts, you can ask me later when we join the next class. Okay. So after giving attendance, USM in the chat box, exit from here. All third semester students.